The Copenhagen Convention, promulgated by Niels Bohr and friends at the Copenhagen Institute studying quantum mechanics, said, don't worry about what quantum mechanics means. Just do the math. There's nothing there. And someone pointed out in my last video regarding many worlds, many waves, many worlds, that the many-world hypothesis of Hugh Everett was essentially untestable. And I agreed, but also, and said that it's within the realm of philosophy, not science. However, I also mentioned that that's the case, or was the case, for atoms. For quite some time, people believed that atoms would never be verifiable things. Scientists believed that their model of the world worked better if they thought of these things called atoms, but whether they were real or hypothetical, just a way to make things work, make the math work, was not verifiable. And the reason is they couldn't imagine a mechanism for testing this hypothesis. But technology changed, and then they were able to. By the early 20th century, we were exploring the structure of atoms. We were looking at the nucleus. That's right, Ernest Rutherford was shooting helium nuclei, that's the center of the helium atom, at gold foil. And it was going through, and then all of a sudden deflecting, and then bouncing back like a cannonball. Like a cannonball bouncing back. He said it was like a cannonball bouncing off tissue paper. We were learning about the atom. And guess what? Nobody doubted that we would know about the atom anymore, because the atom became real, because technology had changed, knowledge had advanced. Now, what has been interesting for me, because when I was going to school in the late 1970s and early 80s, I was told in general chemistry class that we would never ever see an atom. We believed them by then, that wasn't that long ago, but we would never see them. And I was told the next year in organic chemistry class that there were only 3 forms of pure carbon. There was diamond, there was graphite, and there was amorphous carbon. And that's it. And this had been known forever, and that was it. Well, one of the amazing things that happened was, while I was still a student, is that I got a copy of Scientific American, and on the cover was a picture of an atom. And I knew immediately that this was revolutionary. Now, it didn't get in the major media in any way, okay, just in the science journals. But it was earth-shaking. I took it to the professor that I was doing research for, and I showed it to him. I said, well, no, I didn't show him right away. I said, they've got a picture of the atom. And he said, go away, Richard, go away, because he knew that was impossible. It was impossible. Why? Because everybody knew you cannot visualize an atom. Because to visualize something, the wavelength, that's the distance between the crests of the wave, has to be at least as big as the object you're trying to visualize. Now, regular light won't do that. Even using electrons, which behave as waves, won't do that. Even with gamma radiation, we knew no way of doing that. But suddenly a whole new way had developed that no one had thought of before. And I showed him the cover, and his jaw dropped, and he paused for a minute. He didn't say a word. He just grabbed the magazine from me, went into his office, shut the door, and read the whole article. and then told me how amazed he was. And I knew he would be. I was. This was earth-shaking. And what had done it was something called the tunneling electron microscope. And it was a principle that no one had thought of before, even though it could have been done for a very, very long time. They took a needle and they hovered it over the surface of an atom, which is clouds of electrons. Now, those electrons are not supposed to be able to jump into the needle. But what happens is quantum mechanics allows it. It's called tunneling. And what happened is that by moving the needle up and down as you went over the surface of the atoms to maintain the same current, tunneling current of electrons tunneling into the needle, they could get a contour map of atoms. And from there, the technology grew. In a few years, IBM was manipulating atoms with this tip, creating IBM in atoms. It was astounding. The second thing that happened, and this was just shortly after I graduated, is that a new form of carbon, a new allotrope of carbon was discovered, and that's called buckyballs. And the reason why no one had discovered it before, because it's on Earth and it's out in space, is because everybody knew that it didn't exist. Because if it had existed, somebody would have discovered it. And they couldn't think of what it could be. And it turned out it was a ball of 60 carbons that has a geometry like the old-fashioned soccer balls, with pentagons and hexagons all around. And it's a very stable structure. And they found evidence of it. They found evidence of it in candles burning. When you burn carbon, it forms. And they found it out in the stars, where supernova had exploded and carbon had cooked. It formed naturally because it was so stable. And this was earth-shaking, and it still is, because it opened a whole new branch in organic chemistry. Organic chemistry didn't have any really big branches growing in its tree, just little sprigs, twigs, whatever. And all of a sudden, you had this whole new branch. And it led to nanotubes, which are used in composite material. They're being now applied to nanotechnology, the study of the very small. They're using them in electronic devices. And there's a huge number of applications for this new development that we never thought would be around. And there's lots of other stuff just like that. Now, this leads me to think about a few other things that we know about that can't be done. For instance, my favorite book is this. Gödel, Escher-Bach, An Eternal Golden Braid by Douglas R. Hofstadter. A computer science guy. This is about artificial intelligence. And what he's saying is that if we just scale up the complexity of mathematical equations and loop them around in this hugely recursive, chaotic way, that if we do it right, consciousness will develop. And it doesn't matter if it's a biological system or it's some kind of electrical system or a combination of both, you will get consciousness. Now, the problem with this is it reminds me of a cartoon. I love this book, but what you have is you have a professor who's by a blackboard. And then what happens is on one side of the board, there's all these equations. And then on the other side of the board, there's all these equations. And in the middle, there's a line that says, and a miracle occurs. And a scientist standing next to him says, you need to be a little bit more specific in the middle part. That's what this is like. It all makes perfect sense. There'll be this huge phase transition into consciousness if you just keep upping the complexity. But you know what? A lot of people don't believe that. It seems that with classical laws of physics, and that's all he's using here, it doesn't seem like we'll ever be conscious. We'll ever get to consciousness that way. It seems like something would be missing. You just get more and more complexity, but where would that sudden something, that awareness come into being? And now a brief aside. Richard Feynman, a brilliant physicist, used to ask his students, when you look in the mirror, why is it that the top and the bottom of your image are in the top and the bottom, but the left and the right are inverted? Now, of course, you all know I'm far less brilliant than Richard Feynman. But I want to ask you a question. And I'm not inferring anything about your intelligence here. Why is it that human beings debate whether they have free will or not, but nobody debates whether they're conscious? Back to work now. Many folks believe that to attain consciousness we need something more. And that more is quantum mechanics. Roger Penrose wrote a very interesting book called The Emperor's New Mind, in which he proposed a method using microtubules to achieve this. Now, even though we don't really understand how quantum mechanics could allow us to be conscious, many people believe that unless you employ some other technique, you'll never get there. Quickly, we've discovered that photosynthesis is more efficient than we ever expected, and we found it operates by quantum mechanical principles to achieve that efficiency. The way we detect things by smell is a quantum principle. We don't use molecular shapes, we use molecular vibrations, and we detect them using quantum mechanics. So consciousness may require more than just classical physics, and more will come later.